Hey! Don't want that. We're getting ready to talk about section 2.5. Don't need that anymore. Let's close that. Cool. Cool. So far, we covered 2.1 through 2.4. I only said I was going through 2.3, but 2.3, I keep failing to update my notes. The second derivative used to be part of 2.3, and it's not in the new edition of the book, and so we already covered 2.4. There's a bunch of homework posted already. Here's a couple things that I didn't talk about that I wish I had. Here's an example. Let's let g of x be sine x. Let's approximate g prime of pi. There's nothing important about this example other than I want to do one that forces you to make sure your trig settings are correct in your calculator. Hey, you're in a calculus class, and when we do calculus in trig, when we do trig in calculus, we always have our trig function set to radians. So if you have a calculator like mine, hit what is it, mode? I just hit it. Mode? Yeah, mode. The third setting down on mine, I don't know where it is in yours. Check that you're in radians and not degrees. The rules of some calculus rules are way, way easier if you use radians instead of degrees. So we always use radians in calculus. So double check that you are set to radians. I need to pick, so to approximate g prime of pi, I need to pick a number very close to pi. 3.14 is a number pretty close to pi. Hey, if you didn't know, 3.14 is not equal to pi. G prime of pi is about g of a number very close to pi minus pi itself divided by 3.14 minus pi. And I need to stick all this in my calculator. Let's look at our calculator. Oh, hey, before I keep going, let me double check that the stream is actually live by looking at it on my phone. Hey, I'm live. Don't, stop. Okay, we did it. I'm gonna hit quit. I need to calculate sine of pi. Hey, there's a pi button above the to the button. If you've been using 3.14 all your life, that's not going to be good enough in this context. I need sine of pi minus sine of 3.14. And now I need to divide that by, parenthesis, pi minus 3.14. And that gives me negative point, oh man, that's a lot of nines. 6 nines and then a 5. Negative 0.9999995. A number that is so close to negative 1 that it would be a miracle if the derivative at pi wasn't exactly negative 1. And it is. It looks like it's exactly negative 1. Here's our approximation. Here's our guess what the real value is. Rounding that off to 5 decimal places is a reasonable thing to do. And say it's about negative 1. It turns out that it equals negative 1. Sometimes it's really hard to know when we're talking about equals and is approximately equal to. We haven't done the math to verify that if we put more and more digits of pi in there, the answers will get closer and closer to negative 1. And the math of doing that is very hard. But I have so many nines there, I am convinced. Like, we only used 2 digits of pi here, and we got 6 digits of negative 1. That's craziness. Okay. So that's an example just to emphasize, hey, have a calculator and make sure it's set to radians and not degrees, because that's going to mess you up if it's not. I also wanted to do another example with concavity. I'm going to sketch a function. Let me grab some graph paper. Do I have my graph paper open still? No, it's over here. Oh. Let's copy some graph paper to this note. My favorite thing about teaching with tablet, as I have infinite graph paper. Oh, here's our function. Question. On what intervals? Let's call this function h of x. Let's label the axes. I guess I don't need to label the y-axis for this. On what intervals is h prime of x positive? When is h prime negative? When is h double prime positive? When is h double prime negative? What do we know? We know from last time that the derivative is positive. This is when the function is increasing. Let's use purple for answers. The derivative will be negative when h is decreasing. The second derivative will be positive. This is the one about concavity. So this will be when h is concave up. And this will be when h is concave down. So when is the thing increasing? Well, out here at the right, I'm moving up. We always think of the x-axis as being time if we use time-like questions like increasing. And the forward motion of time will be the forward motion on the x-axis. We're always moving left to right when I think about the words increasing, decreasing is where I'm headed to. And as I come in from the left, we are going up, 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 up. Eventually we start going down. Where did we switch going from up to down? Looks like it's right here, which is just a little bit less than 1. So it looks like h is increasing from to the left of 1 as an interval that's negative infinity to positive 1, not a negative. People make a big deal about the brackets and parentheses. In this case, I guess the parentheses do matter. Assuming that point is at exactly 1, which, I just drew this by hand, so it's probably not, but let's pretend that's exactly at 1. Well, I'm asking, when is the derivative positive? The derivative is positive when the thing is increasing. At 1 itself, the graph is totally flat. I would guess that if that's at exactly 1, then the derivative at 1 would be 0, and 0 is not positive. So we don't include the 1. And we never include infinities because infinities aren't numbers. So it's positive here, and it's also positive again later when the thing starts increasing again. It looks like, we'll call that 10. There's more increasing. So here and 10 to infinity. Parenthesis, parenthesis for the same reasons. When is the first derivative negative? Well, that's in here is the downward going part, so that's from 1 to 10. Boom, boom. When is it concave up? When is it concave down? Concave up and concave down are about smiley versus frowny. I want to know, when are you smiley type? When are you frowny type? I draw a smile like this, but this is concave up and this is concave up. Basically anything that when you put the dots above it looks happy is concave up. This is concave down, this is concave down, this is concave down. All of these are concave down. The most common wrong answer is to say you are concave down for this part, which is true. If I look at this face and this face, they are all frowny faces. The graph is bending downwards. It looks like it's going to be bending downwards forever to the left. Although maybe it's getting straighter and straighter, who knows. It's definitely bending down for the part we can see. Over here, it is still bending down. This is still a sad face. Still a sad face. It's going to get happy at some point. I'm smiley over here, and I'm frowny over here. Somewhere in between we switch. Finding the exact spot where you switch is way trickier for concavity than it is for increasing, decreasing. When the function switches from increasing to decreasing, I can see exactly where that dot is. I am dead on balls accurate that that is at 1 where it switches from increasing to decreasing. And I can actually see it's a little bit left of 1. Seeing where the concavity switches is way harder to do with just your eyeballs. It looks like it's around here. If I cut it off here, I think maybe all of this is bending downwards and all of this is bending upwards. But if this was an exam and you said this or this or this or this, I would feel bad taking off points if you put any of these as our answer. I'm going to put it at, call that 4.5. Is where it switches. And the place where it switches, this is called an inflection point. An inflection point is where something switches concavity. It goes from speeding up to slowing down, or from slowing down to speeding up, or something like that. It didn't switch between decreasing and not decreasing here. We were decreasing before the inflection point, and we are decreasing after the inflection point. But before the inflection point, we were decreasing faster and faster. And now we are decreasing slower and slower. We are still decreasing, yeah, and that's what it switched. So when is the thing concave up? It's after 4.5. Our answer here is 4.5 to infinity, parenthesis, parenthesis. When is it concave down? That's from negative infinity to 4.5, parenthesis, parenthesis. Right. If I have a picture, I can look at it and see where it's increasing, decreasing, concave up, concave down, and the information that that tells me about the first and second derivatives is when the things are positive, negative. Right. Cool. I want to tell you a fact. This is crazy interesting. If you've had an algebra class, presumably you've seen exponential growth. Something has exponential growth when it is increasing faster and faster. Population sizes are the biggest examples of population growth, or, biggest for math teachers anyway. And the reason population growth would be exponential is the place that a population increases from is from having babies, and the bigger the population is, the faster it can have babies. Like 100 geese can lay more eggs than 20 geese. So when the population is bigger, it should be steeper than when it was small and it was flatter. So the more there are, the faster it'll grow. And that's usually as far as you get in an algebra type class thinking about population growth. The thing is, though, if these geese live in a pond, there is some limit to how many geese can fit in the pond. The graph is going to flatten out at some point. We just learned this word inflection point. Most population growth curves, so when you get a step past the exponential model, you say, well, it's more like this thing. It's called a logistical model sometimes. There's different versions of it. People are looking at these graphs you'll see graphs like this for the total number of people infected with coronavirus in the news these days, probably. Presumably, it's going to flatten out at some point as new infections stop, and where is the inflection point going to be is a big deal. I don't want to talk about that one right now. I want to talk about human population over time. Population growth, just like geese, should be exponential most of the time, but scientists don't know what is the maximum population that Earth can sustain. This is a big point of argument, and largely it depends on technology. Like, if we get better at making food with less land, then we can fit more people on the Earth. I don't know that we really want to convert all land on Earth into food production, except for the land that has the maximum number of people. Like, that sounds like a pretty crummy world to live in. Scientists don't know what the maximum population on Earth is going to be, but it is much easier to know when is the inflection point going to happen. That's going to be sooner. If I had a room full of students in front of me, I'd ask you, hey, when do you guess that the inflection point of human population on Earth is going to be? And someone always guesses 2050. 2050 is a very popular year for something in the future to happen. And I would stun everybody by saying, no, it happened in the 80s. It was maybe in 1986. And it is pretty weird. We live in weird times. Like, I say this every year, even years where I'm not sitting in my closet lecturing through the internet. Times are weird. Like, when I was in college, we talked about we're living in a post 9/11 world. Maybe we are in the post smartphone world. Like, it seems like a big deal that I have a device in my pocket capable of communicating with any human being on the planet. If I know their name, I can probably look them up and send them a message right now. That's weird. Um, I sort of wonder, what are people going to be talking about our times in 1,000 years? In 10 years, yeah, this is the post 9/11 world, or maybe it's the post smartphone world, or it's the soon we're going to be in the post coronavirus world. I think in 1,000 years, this will be the most significant event that we have lived through in our lives. This is the fastest growth of human population ever, unless somehow the population takes a nosedive and does another big weird switch, which usually is a funny joke in non-coronavirus times. Um, yeah, that's weird. There's a good chance that this is the only inflection point of human population that will ever happen, and we're living with the people who were born in that world's largest class of human beings. There's a chance 1986 had more humans born than will ever be born, or something like that. It's not just births; it's births minus deaths. Was at its largest in the 80s. Anyway, that's an inflection point. That's a graph, reading when it's concave up and concave down, knowing what those words mean. Yeah, cool. Let's get into 2.5. 2.5 is our first of many businessy specific examples. Actually, let me double check that I have the sections right. 2.5 is, yes, marginal cost and revenue. Let's talk about marginal cost and revenue. I'll tell you the punchline to this lecture is marginal means derivative of. If you learn one thing, that is the thing you should know. We have yet another word for derivative of, and it is marginal. The derivative is the margin, or it is the slope of the tangent line, or it's the rate of change, or the instantaneous rate of change, or there's all these words that mean derivative. This is one more to throw into the list. What's a cost function? A cost function, usually it's going to be written C of Q with a capital C, and it gives the total cost. Like in these hypotheticals, we run a business. This is a business calculus class, so we return to these specifically businessy examples pretty often. C of Q is the total cost to produce Q items. Lowercase q is for quantity. C is how much does it cost to make that quantity. And R of Q is our revenue function. This is the total revenue generated from making and selling Q items. Or I guess the making part doesn't make the revenue. Total revenue generated from selling Q items. That's cost, that's revenue. If you've taken any business class, you know that after I write down cost and revenue, I'm going to talk about profit. Profit, we use a capital Pi as the letter for. At least in this class we do. We use pi because P is going to be price. And we don't want the same letter meaning multiple things. And the tradition when you run out of English letters is you grab a Greek letter. Also note this is a capital Pi, as opposed to the lowercase pi is the one we use for 3.14159, so on and so on. The lowercase pi, you write that with a wavy top. The capital Pi, you write it with a flat top. It's also a little bit bigger. Pi. I don't know how valuable that is. Anyway, that's the penmanship of pi. This is the total profit from making and selling Q items. It might be the net. So, and the fact that is worth knowing is that profit equals revenue minus cost. Revenue is total money that comes in, cost is total money that goes out. All the money we get from selling it minus all of the costs that it took to make it is profit. I guess we could do some examples with that, but let's get to the place where the calculus happens. Okay, so the next step is the derivative of this function. C prime of q will also be called MC of q, is the marginal cost. At a production level of q. So, what does this mean? At a production level of q items, say I have some specific q number of q naught items. What this is telling us is that the rate of change of cost is MC. Let's put some specific numbers on here. Let's say MC of 500 is 30. This is telling us that when we make 500 items, our cost is increasing at a rate of $30 per item. Remember, the units on a derivative, and this is a derivative, C prime of 500, are y units per x unit. C is cost, is going to be measured in dollars. Q is production, is going to be measured in items. It might be measured in thousands of items in some situations, but mostly we're just going to measure things in items. So our cost is increasing at a rate of $30 per item. Keep in mind, this isn't telling us that it has cost us $30 per item to make these 500 items. That's a different thing. That'll be called average cost. That's not what the rate of change tells you. The rate of change, think about that area of a house example, is talking about the cost not of making earlier items, but of making additional items. So it's the items near the 500th that cost about $30 a piece. There's a standard businessy way of thinking about this. We say MC of Q, or MC of 500, is about the cost of the 501st item. We think about if you make a small number of extra items, and 1 is the smallest number you can make, then the derivative should be giving you about the amount to make the rate at which that goes. When you make it 1 item, the $30 per item becomes $30 for that 1 item. It becomes a nice handy way of changing it from dollars per item to just dollars or something. It is still dollars per item, and it's more accurate to say the first few items cost about $30 a piece or something. And because a derivative can, when I talk about a derivative, I can move a small amount to the right or to the left. There's no particular reason to say 1 more item. It's just as accurate to think about it as 1 less item. So it's also going to be the cost of the 500th item, or that's just as accurate a shorthand approximation of what the margin means. But we're more likely to think of it as the 501st. Like, this is the short, easy, understandable way of saying what the marginal cost means. It's the cost of the 501st item. Similarly, marginal revenue of 500 is the revenue on the 501st item. And M pi of 500 is the profit. Profit with a P, not a pi. So let's get to an example where we have a specific function. Say I have a pencil factory. There's a tradition of every factory we pretend to own will only produce items that are on the table in front of me. Say I have a pencil factory, and our cost function is C of Q equals 50 plus 0.004 Q squared. 1. Let's C of 500. Interpret. How do I find C of 500? I plug a number into a formula. That's not so bad. I need 50 plus 0.004 500 squared. What is this? This is your calculator. What's 50 plus 0.004 times 500 squared? It's 1050. Interpret. Turn this into a sentence about pencils. Our sentence about pencils is the cost to make 500 pencils is $10.50. It costs us $1,050 to make 500 pencils. That's $2 a piece. I guess these might be very fancy pencils. 2. What's MC of 500? Interpret. MC means derivative of. So I'm looking for C prime of 500. And I know how to approximate a derivative. I need to pick a number very close to 500. I'll pick 500.001 minus C of 500. Divide that by 500.001 minus 500. Calculator. Dear calculator, what is 50? Oh, let's write out what that means. This number I already worked out was 1050. This number is going to be 50 plus 0.004 something squared, and my something is 500.001. What does that give me, dear calculator? What's 50 plus 0.004 times 500.001 squared? A number very close to 1050. Subtract off the 1050. Divide that by 0.001. I get 4.0004. A number so close to 4 that it would be reasonable to make a guess that the derivative is probably 4. C prime MC of 500 is 4. How do I interpret that? The standard interpretation is this is something about the 500th something. The 501st pencil. Also the 500th. But usually we phrase this about the next one. The 501st pencil costs about $4 to make. Or additional pencils after the 500th cost about $4 to make. Or the last few pencils I just made at the 500th. The 500th and the 499th pencil cost about $4 to make. It should work both directions. Yeah, that's using margins. Let's get to a profit example. So, example. Suppose my cost and revenue functions are C of Q equals 50 plus 0.004 Q squared, same cost function. R of Q is 10Q Estimate. MC of 500. We already did that one. MR of 500. MPi of 500. MC of 500 we just did. It was 4. That was the last example. This is the same cost function, by the way. Let's do MR of 500. It's about, I need R at some number close to 500, at least 500.1, minus R of 500, divided by 500.1 minus 500 is 0.1. How do I take R of these things? It's 10 times that number. So I need 10 times 500.1 minus 10 times 500. Divide that by 0.1. I can do that multiplication in my head. It'll be 5001 minus 5000 divided by 0.1. This is 1 over 0.1. 1 over a tenth divided by a fraction, multiply by a reciprocal, it's 10. I'm showing off I can do stuff without a calculator. It's okay to use a calculator. Our marginal revenue is 10. The revenue we get on the next pencil will be about $10. I guess I'll take a second and note, hey, this is a really simple function. Our revenue when we sell Q pencils is 10Q. If I sell 100 pencils, I'm going to end up with $1,000 in my pocket. It's really simple to understand what this function is telling us. It's telling us that we're selling the pencils for 10 bucks a piece. These are some fancy pencils. That means that here, like when we talk about derivatives, I'm saying that the rate of change is $4 per pencil. It is costing us $4 per pencil to make these pencils, to make additional pencils, and I want to be clear that I'm not saying that all the pencils we made cost us $4 a piece, or that they even cost an average of $4 a piece. Well, here's the situation where that actually is true. The revenue on the next pencil is $10 because the revenue on every pencil is $10, because our formula is every pencil we are making $10 from it. Probably because $10 is what's written on the price tag, and we are not changing the price depending on how many we're able to make. We're not thinking in those terms. So here's a situation where it's reasonable to glance at that and say the marginal revenue is going to be 10. It'll probably be a while before we're at that point, though. Marginal cost was 4, marginal revenue was 10. What's marginal profit going to be? To find marginal profit, I need to find the profit at 500.1 and the whatever. I guess it's probably worth it to write down the profit function. If I want to take the derivative of a function, I would like to have a formula for it. Profit is revenue minus cost, so our profit function will be our revenue function minus our cost function will be 10Q minus our cost function is 50 plus 0.004 Q squared. Hey, you need parentheses because you're subtracting the whole thing. It's minus all of cost. This is all part of the cost. So that's 10Q minus 50 minus 0.004 Q squared. So M pi of 500 is about pi of, let's use 500.1 minus pi of 500 divided by 0.1. That'll be, how do I plug 500.1 into this? It'll be 10 times 500.1 minus 50 minus 0.004, 500.1 squared. That was this part minus, now I need this part. I want to wrap it in parentheses because I need to subtract the whole thing. These red parentheses don't matter, but the blue ones do. Minus, oh hey, I told people they can text me if they have questions if they're watching this live. Is anyone watching this live? I don't. Anyway, live chat has a chat thing in it, but I only have the one screen here, so it's hard for me to keep an eye on that. If you want to say something, if you're watching live and you want to say something, say it in the texting. Minus the whole thing. These blue parentheses do matter. Plug in 500 now. I need 10 times 500 minus 50 minus 0.004 500 squared. Close out those blue parentheses. All of this divided by 0.1. This is going to be rough to stick in a calculator. Give me 10 times 500.1 minus 50 minus 0.004 times 500.1 squared. That's the first part. Minus, I'll put these parentheses because these ones matter. 10 times 500 is 5,000. Minus 50 minus 0.004 times 500 squared. That's minus the blue parentheses. Divide all of that by 0.1. I get 5.9996, a number so close to 6 that it would be reasonable to guess that m-pi of 500 is probably 6. Or probably is that 6 is the number that this is going to get closer and closer to. I can change this 500.1 to a 0.01 and a 0.001 and see if I get more and more 9s here. And that'll convince me that my thing is 6, but I'm convinced right now. In general, so sometimes the problems, hey, I should tell you. Sometimes I will tell you, repeat until you are sure you have 3 digits of accuracy. If I don't tell you that, don't stress too much over how many zeros should I put. Don't go crazy. If you put 1.0000001, your calculator is probably going to give you too much error for that computation to be meaningful. Just put a few zeros and assume that's enough. Or if I tell you, make sure you have 3 digits of accuracy. That's when you know you need to do it a few times and see that those digits are not changing over time as you add more zeros or 9s or whatever you're doing. Okay, so the marginal profit of 500 is 6, and we've answered the question. And now here's the place where I make students mad by saying, hey, look at all this work we did. We didn't have to do this. Because what is this marginal cost telling us? It's telling us the 500th item costs $4 to make. And this is telling us the 500th item is going to bring in $10. If I think about, should I make this item, I can tell that it's going to cost me $4. It's going to bring in $10. If I get $10 and it cost me $4, then my profit on doing that action was $6. The marginal profit does equal the marginal revenue minus the marginal cost. Profit equals revenue minus cost. This is connected to the rule that marginal profit equals marginal revenue minus marginal cost. And this is a thing about functions in general, that if I know the derivative of something, and I know the derivative of something else, that'll be the derivative of the difference. If I want the derivative of a difference of two functions, it is the derivative of the difference. It is the, how do they say this? There's a clever way of saying this that I screw up. The derivative of the difference is the difference of the derivatives. This is one of these rules that feels like it's not saying anything at all. You're going to learn eventually that multiplication and division do not have this nice property. The fact that addition and subtraction do have this nice property, that they are preserved derivatives, is a big deal. And you need to name a rule for that. We don't really give this one a name because it's not a thing that's hard to remember, but if there is, it's a sum difference rule. That's the end of 2.5. And this fact is our perfect segue into Chapter 3. That's the end of Chapter 2. Let's get into Chapter 3. Section 3.1. So, Chapter 3 is Rules of Differentiation. Differentiation is the word for taking derivatives. And Chapter 3 is rough. The thing that Chapter 3 is about is at the end of Chapter 3, you're going to be able to look at a formula for a function and write down the derivative of that function. This is our goal. It makes a lot of the problems we did in Chapter 2 obsolete, where this whole figuring out this difference quotient is not really going to be a thing we need to do anymore after we've learned the tricks of Chapter 3. There will be problems on the exam where I say to estimate the derivative using the difference quotient. The difference quotient, remember, is the name for subtracting and dividing. This is still a thing you're going to have to know how to do for the exam, and then how to do again for the final exam. So don't feel like that skill was wasted, but we're about to gain some new skills. And these new skills are looking at a function and writing down its derivative. And the first rule, this chapter is going to be called the power rule. But before that, we have the sum difference rule. And the sum difference rule is that the derivative of some function plus some other function is the derivative of the one function plus the derivative of the other function. And if it's a minus, then it's a minus. And this rule isn't something you need to memorize. I guess the bigger warning you need to know for this rule is this is a special property of plus and minus. Other times and divide are not going to do this. In general, the rules are hard. This is when it's easy. I guess this comes with the constant multiple rule. If I used f of x plus f of x, I'm learning that the derivative of 2f of x is f prime plus f prime. That's 2f prime. And there's nothing special about the number 2. The derivative of, if there's a constant out front of your favorite function, the derivative, the constant just stays out front of the derivative. If you have a multiple of a function, the derivative is that multiple of the original. It's important that c is a constant here. If c is a function or anything, c needs to just be a number. If c has x's in it, then it doesn't work out. Okay, these are the baby rules. We don't really have anything to use these on because there's no f that we know the derivative of yet. Let's get some f's that we know the derivatives of. Should I write this out? I'm going to write something out. Here's the thing we want to do. The power rule is to figure out what's the derivative for a power of x. If I had a room full of students, the thing I would be doing is saying, find these derivatives. I'm going to write down the function f of x equals x, g of x is x squared, h of x is x cubed, and q of x is x to the 4th. And we're going to compute the derivatives of these at enough points. Our goal is to figure out some rules for derivatives. So we're going to take the derivative at 0, 1, 2, 3, 4, 5, just 4. This is a nice classroom activity, because hey, being able to compute one of these derivatives at a point is like the most fundamental thing you need for exam 1. And so the thing I do is now say, hey, everybody in the class, compute one of these and call it out when you get it, and I'll start writing them down. And if I have enough people, then we can get it in like 2 passes. And there's usually a few people in the classroom who are looking around saying, wait, you guys know what to do? I have no idea what we're trying to do here. And it's good to get a little bit scared that you don't know what you're doing if it's almost exam 1 time and you still don't know what you're doing. Like, that should be a little bit scary. You compute these things and you end up, this one is always 1. For x squared, the answer we get is 0, 2, 4, 6, 8. Here the answer you get are 0, 3, 12, 27, 48. And here the answer we get is 0, 4, 32, 108, 256. And the goal is to figure out the patterns here. This one, the pattern's real easy. The derivative is always equal to 1. The derivative of the function x is the function 1. It is always a constant. This makes sense. Y equals x is a line. The derivative is supposed to be saying, hey, what is the slope at this point? Well, the thing that makes a line is it always has the same slope at every point, and for the line y equals x, the slope is 1. For x squared, this pattern's easy. I got 2, 4, 6, 8. Who do we appreciate? Yeah. The formula is g prime of x is 2x. This number on the right is double the number on the left. It's a line, you work out the slope, you work out the y-intercept, it comes out to be this. It's not bad. The derivative for x cubed is way harder. 0, 3, 12, 27, 48. A thing that makes this helpful to notice the pattern is noticing, hey, all these numbers are multiples of 3. This is 3 times 0, and this is 3 times 1. This is 3 times 9. Wait, no, 3 times 4. This one is 3 times 9, and this one is 3 times 16. Pulling off the 3, like the 3 is like masking a simpler pattern going on, and that simpler pattern is 1, 4, 9, 16. These are perfect squares. These are the numbers I can take the square roots of. And in fact, they are the square of x itself. This is 3 times 9. This is 3 times 3 squared. This one is 3 times 4 squared. This one is 3 times 2 squared. And our pattern here is that the derivative is 3x squared. And similarly, these guys have a factor of 4. 4 times 1. This one is 4 times 8. This one is 4 times 27. This one is 4 times 64. Here it's somewhat harder to notice the pattern, but if you think about what was going on the others, these are cubes. 8 is 2 times 2 times 2. 27 is 3 times 3 times 3. 64 is 4 times 4 times 4. 1 is 1 times 1 times 1, and 0 is 0 times 0 times 0, so it works there too. Our pattern here is that q prime of x is 4x cubed. And now we've noticed 4 separate patterns, and our hope is to stitch these together into one bigger meta pattern, like 2x, 3x squared, 4x cubed. It can help if I call this 2x as 2x to the 1. Maybe it helps to write this 1 as 1x to the 0. I write these out, and then I usually ask the class, hey, can someone figure out what the derivative of x to the 10 would be? And the derivative of x to the 10 turns out to be 10x to the 9. Usually people get that right. And yeah, there we go. This is the power rule. The power rule is that the derivative of x to the n, any power of x is, there's still a power of x, but it's 1 less than the power was before, and you get a number out front, which is what the old number was. This has some special versions. The derivative of a constant is 0. You can think of this constant as a constant multiple of x to the 0. When the 0 comes down, you get a constant multiple of 0. X to the negative 1 is just 0. The derivative of a multiple of x, or the derivative of x is 1. This can be the power rule if I write that as x to the 1, but usually you sort of keep that in a different place in your brain, so it's worth holding that separately. These can sort of be organized together by recognizing a linear function. The derivative of mx plus b, so if you have a multiple of x and a constant, you're basically asking what is the slope of the line mx plus b, and the slope is m. Very often these will come in a group, and it's nice to get these together. The b is a constant whose derivative is 0. This is m in front of a thing whose derivative is 1. So I might think of this as m times 1 plus 0, but that's just m, is the slope of that line. We know the power rule, we know the sum difference rules. We can take some derivatives. Let's do some examples. Oh, hey, let me give you a heads up. You're going to be doing some homework on this. You're going to find a website where you can type in a function, and the website will give you the derivative. Don't do that. You need to learn this stuff. You will see why when we get closer to the exam, but like don't there are ways around actually doing most of the homework problems, but that will not be a good idea in the long run. I'm going to make a post on Blackboard called Information About the Exam that'll answer some of that. I'm trying to remember not to say things in these. I want to make these videos something I can reuse in a year, so I won't talk about your exam too specifically in here. But, don't do that. I'm going to write down a function. We're going to write down its derivative. If I hand you x to the 9, what's the derivative of that? It is 9x to the 8. If I hand you g of x equals x to the 9 minus x to the 11, I know that sum difference rule. I need what's the derivative of x to the 9? It is 9x to the 8. Minus what's the derivative of that x to the 11? It is 11x to the 10. If I handed you q of x is... Actually, hang on. Let's focus on this one for a second. We've said the power rule. We sort of noticed this pattern, but it feels like maybe... Are we really sure this works? Are we doing this right? It's worth picking a particular function and verifying that, I want to emphasize that this thing we are doing is the same thing that we were doing all of chapter 2. So, if I have this function, I know how to take g prime of 3.6. The way I would take g prime of 3.6, actually, that's too big. Let's make it g prime of... The numbers are going to be crazy big if I use that. Let's take g prime of 1.3. I think that's not that bad. That might be bad. I don't know. The way I would estimate g prime of 3 is I would take g of some number very close to 1.3, maybe 1.3001. I would take g of 1.3 itself, and I would divide that by 1.3001 minus 1.3. What do I get when I do that? Do your calculator. What's my function? My function is x to the 9 minus x to the 11. So this is 1.3001 to the 9 minus 1.3001 to the 11 minus 1.3 to the 9 minus 1.3 to the 11. Divide all that by 0.0001. There's an extra 0 because we're that far from the decimal point. Hey calculator, what is 1.3001 to the 9 minus 1.3001 to the 11 minus, parentheses around the second part, 1.3 to the 9 minus 1.3 to the 11? We've subtracted and we need to divide by 0.0001. Oof. Really? I still have a crazy big number. Did I screw this up? Oh, I had 13.001. Second enter. Second enter. Okay, that should have been 1.3001 to the 9. Let's try that. That thing divided by 0.0001. Cool, I'm getting negative 78.264. I could do this a few more times and feel like I have more digits of accuracy. I think the derivative is somewhere around negative 78. I don't really know how many digits of this are accurate. These were really big numbers, so maybe this isn't that accurate. But, allegedly, this is a formula for all of g prime. If the power rule works, then g prime of 1.3, the thing we estimate by doing this, should be computable exactly by doing this. G prime of 1.3, RU 9 times 1.3 to the 8 minus 11 times 1.3 to the 10. Are you? I'll stick you into my calculator and find out. What is 9 times 1.3 to the 8, no, to the 8 minus 11 times 1.3 to the 10. That one is negative 78.228. It turned out we had this much digits of accuracy. And this one is an exactly correct answer. We're not getting an approximation that we would have to redo over and over to feel like it's right. The thing we start doing in Chapter 3 is getting the exact derivative with all the digits right away. This is a big deal. Hey, remember that first example when we had y equals x squared? We had f of x equals x squared. We had f prime of 2, and it turned out to be 4. Well, we've learned the power rule. F prime of x is 2x, and f prime of 2 is 2 times 2. Sure enough, it is 4. The thing the power rule is doing is the same thing we were doing back in Chapter 2, except now we're doing it at every point, all at once, with all the accuracy immediately. Like, the power rule is a big deal. Why did we have to learn all that Chapter 2 stuff? Learning that Chapter 2 stuff is about learning what the derivative is and what it means. Now, the calculus begins with, okay, here's how you do these computations directly. Like the word calculus was given the name of calculus because it makes us able to do these calculations quickly and accurately, and like that is the calculus part of calculus. Let's do a couple more basic power rule versions. I'm going to stop lecturing in 25 minutes. I guess we'll finish this section. If I write down the function g of x equals x plus x squared minus x cubed plus x to the 8 minus x to the 11, and I say differentiate. Differentiate is a word that means find the derivative, or take the derivative, or whatever. What's the derivative of this? Derivative of this might help me to write this as x to the 1. The derivative of that is 1. 2x minus 3x squared plus 8x to the 7 minus 11x to the 10. Cool. Let's try one with some constants. If I hand you h of x is 4x to the 8 minus 9x to the 6 plus 11x squared minus 22x plus 7. Okay, there's a step in between that we're usually not going to write. I'm going to put this in a thought bubble because after this example, we're never going to write this step down. But the step is, this 4 is a constant out front. A constant out front stays out front. It's going to be 4 times whatever the derivative of x to the 8 is. What's the derivative of x to the 8? It is 8x to the 7. Minus 9 times, what's the derivative of x to the 6? The derivative of x to the 6 is 6x to the 5. Plus 11 times, what's the derivative of x squared? Derivative of x squared is 2x. Minus 22 times, what's the derivative of x? It's 1. Plus, what's the derivative of 7? 7 is a constant. His derivative is 0. You might be thinking about what does y equals 7 look like. It is a horizontal line. Its slope is always 0. Or you might just group all of these together and say this is a line whose slope is negative 22, so his derivative here will just be negative 22. There's a few ways of organizing this step in your head. However you want to think about it is fine, as long as you're getting that it's the negative 22. This thing now simplifies. This is 4 times 8 times x to the 7, and I can do 4 times 8. It's 32. 9 times 6 is 54. 11 times 2 is 22. This is our derivative. We're not usually going to write this in between step, because it's not too bad when I pull the 8 out front to just multiply the 8 by the 4 in my head and write 32. 6 times 9 is 54x to the 5th. 2 times 11 is 22x. So there's this step of multiplying by numbers that we traditionally don't write out. If you feel better writing it out, go for it. Especially if you make multiplication mistakes. Like, yeah, anyway. Here's an example. If I hand out h of x is 4x squared minus 8 times x minus 1. How would I take the derivative of this? What's the derivative of 4x squared minus 8? It is 8x minus nothing, 8x minus 0. I am often going to write down this minus 0. The minus 0 doesn't do anything, and you don't have to write it down, but I find that it helps me to have written it down so that I don't later think I forgot part of it. I'll usually not write it on the step after that, so, I mean, you don't need to write it, by the way. What's the derivative of x minus 1? The derivative of x is 1. Derivative of 1 is 0, so this derivative is 1 minus 0. So maybe the derivative of this thing times this thing will be the derivative of this times the derivative of this. But no, it turns out that is not correct. Plus and minus are special. The fact that I can just ignore these pluses here and take all these derivatives one at a time and leave the pluses and minuses there is a rule, not a thing that is automatically true. And I mentioned at the time, it's not true for times. The rule for the derivative of something times something is going to be called the product rule. I'm probably going to lecture about it tomorrow, and it is rough. It is not as easy as this. So why am I giving you this problem if you don't have the product rule yet? The reason I'm giving you this problem is you can do this problem without the product rule. And once you have the product rule, you're always going to use the product rule, but sometimes you'll realize, dang, I knew a simpler way to do that. Let me remind you right now, hey, you have a simpler way to do this, which is you can do this multiplication. If I FOIL this out, first 4x cubed outside minus 4x squared inside minus 8x last plus 8. This is a thing I can take the derivative of. The derivative of this is 12x squared minus 8x minus 8 plus nothing. That's it. I'm not writing the plus 0 right now, I guess. Cool. I have made another mistake. Pause the video and see if you can see this other mistake. The mistake I have made is not a mistake in taking the derivative. The function is this. The mistake I have made is an abuse of the word equals. This thing does this. There's a lot of math problems you do where you write this equals this equals this equals this. Now it's simplified, box around it, that's the answer. And you get into a feeling of doing that in problems like this, especially where you have to rewrite the original function. And the mistake I have made is to say that the original function equals its derivative. The step from here to here is not an equal step. We're not simplifying it. We're not factoring it. We're not rewriting the same thing in a new way. This is a different function. It's the derivative. From here to here, I am rewriting the same thing. And if I didn't write h of x there, that would be fine. Just writing h of x equals this is okay, because the step here is not doing something. From here to here, this is not leaving it the same. That's the original. This is the derivative. You want to avoid writing that a thing equals its derivative. That leads to big mistakes. I worked as a math tutor a bunch, and I've seen a bunch of people, like this is a mistake lots of people have made, where they have y equals 3x squared minus 4x plus 2. And they're trying to take the derivative of it, and the derivative is 6x minus 4. And they're in this rhythm, I got real stylus problems right now, 6x minus 4. And they've gotten into the rhythm of this equals this equals this equals this, so they just keep taking derivatives. Derivative of that is 6, derivative of that is 0. Boom, box around the 0. That is not what we're trying to do. This is y prime, this is y double prime, and this is y triple prime. Y triple prime does equal 0. Maybe there will be places where you want the third derivative of a thing, and if it's 0, maybe that's something useful to know. Anyway, heads up, be careful of that. I'm gonna blow my nose. Give me 1 second. I'm back. Cool. So we got the basics of the power rule down. Our next thing we're talking about is still just the power rule, but the thing I want to observe is the power rule works even on, so far every exponent we've done was a positive whole number. I guess we did x to the 0, x to the 1, x to the 2. There's numbers other than 0 and 1 and 2. X to the 1/2, or x to the -3, or x to the -21/16. These are also powers of x. And the same power rule works on them. If I hand you y equals x to the 1/2 plus x to the -3 minus x to the -21/16, the derivative of this is something you can find, dy dx. Hey, sometimes I'm calling it y prime and sometimes I'm calling it dy dx, and this doesn't mean anything. I'm just going to keep using them both so that we're comfortable with all those words. There's not some special difference between the two types of problem. They're all just write down the derivative. If I want to write down the derivative of that, the rule is, it can be helpful to write down x to the 8. The derivative of x to the 8 is 8x to the 7. Notice I was careful to use a symbol other than equals. If I want a short way of saying derivative of this is that, sometimes I'll use an arrow. I'm being careful to not say it equals, but the connection, it's a real pain coming up. Like the correct way of writing it is the derivative of x to the 8 is 8x to the 7. But this is like really wordy, so I'll sometimes just use an arrow to mean derivative. And the main thing is don't use an equals to mean derivative, because they are not equal, they are different things. What's the derivative of x to the 1/2? The 1/2 comes out front. X to the new exponent is that minus 1. What's 1/2 minus 1? This is legit harder to actually subtract this in your head. I need a common denominator. 1/2 minus 1. 1 is 2/2. 1/2 minus 2/2 is -1/2. This is going to be 1/2 x to the -1/2. In the next week, you're going to get really good at subtracting 1 from fractions in your head. Like, this is going to be a thing you get pretty good at. Plus x to the -3. -3 comes out front, plus -3. That looks dumb. This is the same as -3. You're also going to get in the habit of don't write the plus until you're sure it's not in the minus. Minus 3x to the, what's my new exponent? It's -3 minus 1. What is -3 minus 1? Right, you got to remember subtracting makes it even more negative. We end up at -4. Minus -21/16 times x to the, oh geez, what is -21/16 minus 1? Is -21/16 minus 16/16. -21 and -16 will be even more negative. -37/16, I think is correct. Yeah, there we go. Here's a formula for the derivative. It's the same power rule. We're still just multiplying by a number and subtracting 1 from an exponent. The subtracting 1 is legit harder than it was just a second ago. There are some numbers that are harder to subtract 1 from, but you're still just subtracting 1, so you're sort of not allowed to complain about it. 21/16 is a pretty rough example, but yeah, we're subtracting 1 from these things. Wait a minute. Don't these exponents mean something? Yeah, they do. X to the 1/2. Come on, Ben. X to the 1/2 meant the square root of x. If you have x to a power... hang on, I gotta switch the battery out in my stylus, I think. This is dying constantly now. I think one of these batteries might be better than the other, but I don't know which is which. bought a special USB quadruple A battery charger that runs on USB. But then it turned out I'm using both my USB slots in my laptop for my mouse and my headset. So I had to bring in a, yeah, whatever. In general, if you have x to a fraction, the thing you're doing is a radical and a power. And it's a power of m and a radical of n. This is the nth root of x to the m. The order doesn't matter, nth root of x to the m. Often this is the easier one to compute, and this is the easier one to write down because you don't need the parentheses. But they are the same as long as x is positive, and the times where they're different are when the m over n could have reduced and it didn't reduce. We don't care about that, don't worry about that. What does a negative exponent mean? X to the negative 1 means 1 over x, and in general, x to a negative anything means 1 over that power of x. These two rules will combine when you have a negative fraction. If I have x to the negative 2/3, that means the negative is 1 over. The power of 2 is an x squared. The over 3 is a cube root. So x to the negative 2/3 means 1 over the cube root of x squared. These are some rules of exponents that you need to know to do these problems. And the reason you need to know them is that if I write down y equals the square root of x plus 3 over x to the 5th plus 2x to the 7 minus 8, you need, and I tell you to differentiate it, you can do that. It's just the power rule, but you need to be able to rewrite these things as powers. Square root of x means x to the 1/2. Dividing by x to the 5th means this is a power of x to the negative 5. The 3 is still a 3. This is still 2x to the 7 minus this is 8. It'll be tempting to write down 14x to the 6 minus 0 here. I'm not doing that because I'm not taking the derivative. This is the part of the reason that I make a big deal about write down y equals and write down y prime equals, is you need to keep in mind the whole way through the step, am I differentiating this yet? Right now I'm not differentiating because I needed to rewrite this thing. I didn't differentiate it right away. I had to rewrite these things in such a way that I'm ready to use the power rule. And now I am ready to take a derivative. Derivative of x to the 1/2 is 1/2 x to the, what is a half minus 1? That's a half minus 2/2. 1 minus 2 is negative 1/2. In general, you're looking at numerator minus denominator is what's going on when you, is the new numerator. When you subtract 1 from a fraction. Negative 5 times 3 makes negative 15. X to the, what's 1 less than negative 5? It is negative 6. 7 goes down out front. I get 14 x to the 6 minus 0. That's it. I'm done. Here's our answer. Yeah, that's about as bad as this gets. Let's try a new one. If I write, here's the thing that gets real confusing. 4x cubed minus 8x squared plus 17x plus 11 minus the cube root of x to the 6, not 6, x to the 7. What's the derivative of this? The derivative of 4x cubed is 12x squared minus 16x plus 17 plus 0 minus, what is this? This is x to the 7/3. I have made a mistake. The mistake I have made is I didn't take a derivative at that step. I was rewriting the function in order to take its derivative. If I've already started taking derivatives the whole way through, that's the time that I am most likely to make the mistake of, like it feels like when I look at this, the thing I'm supposed to write down is that, but writing down that isn't taking the derivative. In this situation, where I haven't left myself a space to rewrite the whole thing, and I kind of don't want to rewrite the whole thing, what I like doing is a little thought bubble here, where I write down, what does this mean? This means x to the 7/3. Okay, now I'm prepared to write down the derivative. The derivative is minus 7/3 x to the 7/3 minus 1. 7 minus 3 is 4. My new exponent is 4/3. So this is y prime. Keep in mind whether you are taking the derivative now or you're going to take the derivative later. Yeah. Let's do one more example that sort of shows off some of the cool things we learned from chapter 2. H of x is the square root of x. Let's find h prime of x. 2, let's find h prime of 100. 3, use that to estimate the square root of 100.12. The third one is maybe not clear what's going on. We'll get to that when we get to that. Part 1 is easy. This function is x to the 1/2. By hand. The thing we're doing is, by hand, we're approximating the square root of 100.12, which feels like a really hard thing to do by hand, but we're going to get a really impressive estimate. That function is x to the 1/2. What's the derivative of x to the 1/2? It is 1/2 x to the negative 1/2. 2. What's h prime of 100? Well, it's 1/2 times 100 to the negative 1/2. It'll be tempting to stick this in a calculator, but the thing that we're doing by hand is more impressive if we do it by hand the whole way. So let's do that. This is 1/2 of negative exponent means 1 over 100 to the 1/2. A power of a half means a square root. So I need 1/2, 1 over square root of 100. I know the square root of 100, it's 10. So this is 1/2 of 1/10. That's 1 over 20. This is 1/20th is 5% is 0.05 if I wanted a decimal for some reason. I can do that derivative by hand and it's not that bad. 3, the square root of 100.12, that means h of 100.12. The thing we learned how to do in chapter 2 is we can use h of 100 and h prime of 100 to estimate h at values near 100. The thing we don't need calculus to do is to say 100.12 is a little bigger than 100. Come on, stylus, don't be bad again. So the square root of 100.12 is a little bigger than 10. This is like a computation, an estimation you can make in middle school or whatever it is you learn about what a square root is. The thing calculus does is if we can find the derivative, and now we can by hand, we can use that to say something about how much bigger it is than 100. This is that new y, old y. The scheme we write this up as is new y value is approximately the old y value plus the derivative times the change in x. We want to know what is h of 100.12. This format is telling us it should be about h of 100, which we can do. I know the square root of 100, it's 10. I guess we didn't write that down anywhere, but h of 100 is, square root of 100 is 10. Plus the derivative, we got that, was 1/20th of the change in x. How much did you wiggle the x by? How much did you scoot over from 100? You went from 100 to 100.12. New value minus old value is 0.12. The square root of 100.12 is about 10 plus 1/20th of 0.12. Can I do this in my head? 0.12 is 12 over 100 times 1 over 20 That's, let's cancel that by 2. Let's make that 6 over 1,000, because that's a number I can rewrite as a decimal. So I'm just going to cancel the 2 here and get 6 over 10 times 100. 10 times 100 is 1,000, so this is 10.006, I think. We're working out that the square root of 100.12 is about 10.006. How close were we? I love these problems. Yeah. Square root of 100.12 is this. Actual retail value. Do people your age still watch The Price is Right? The Price is Right, they reveal the answer. And the answer is the actual retail value is, what's the square root of 100.12? It's 10.00599982. How far off were we? If I subtract our guess was 10.006. We're off by this 1 point. So if you haven't seen it before, this is writing something in scientific notation. The E means 10 to the. So we're off by 1.79 times 10 to the negative 6. That says move the decimal place back 6 times. 1, 2, 3, 4, 5, 6. We were able to estimate the square root of 100.12, and we were off by 0.0000179. That's crazy. That's a crazy thing to be able to do in your head. Be a little bit impressed. That's a thing you can get from calculus. Okay, that's the power rule. That's the end of 3.1. You should be well into the homework for chapter 2 by now. Those due dates, I don't know what I put for those due dates, but I think I put everything due Friday. We're going to have the exam this Friday. I'm going to post information about the exam. I'm not sure what's going to be on. It's whatever we get through tomorrow is what will be on the exam. What's today? Is today Tuesday? Yeah, I'm a little ahead on the lectures. Whatever we get through by the end of tomorrow is what's going to be on the exam Friday. There will be some time Thursday for questions or whatever. Check Blackboard for exam information. There's like good information there. There's some good news, but I'll post that later today. I'm going to sign off. I'm going to